Hi, the last class we considered plane electromagnetic waves, and if the electromagnetic wave is traveling in z direction, then we know the electric field point in the, and if the electric field is pointing in x direction, electromagnetic wave advancing, propagating in z direction, and electric field is pointing in x direction, then we know the magnetic field will be pointing in y direction. The complex amplitude of the magnetic field B0. Okay, complex amplitude of the magnetic field B0, that is equal to k by omega z, unit vector z, the direction in which the electromagnetic wave is traveling, and cross product with the complex amplitude of the electric field, where the electric field is pointing in the x direction. So due to this cross product, clearly the magnetic field will be pointing in the y direction. K is the propagation constant, omega is the angular frequency. Okay, and we substitute for k and omega. We have seen we can get B0 as equal to E0 by C. B0, that is the real part of the complex amplitude of magnetic field, that is equal to the real part of the complex amplitude of the electric field over C. Okay, the relation connecting magnetic field and the electric field. So in electromagnetic wave, the electric field and magnetic field, they are closely related. They are related by this relation. Okay, so we are now representing the complex electric field associated with the electromagnetic wave. It is E of z t, the complex electric field, E of z t. We know the electromagnetic wave is advancing in z direction. So at a point z, at a time t, the electric field, the complex electric field is given by E0, the complex amplitude, exponential I kz minus omega t, the unit vector x, the direction of the electric field. And magnetic field, we saw that it is in the y direction. So the complex magnetic field B of z t, that is equal to B0 exponential I kz minus omega t y. And V0, the complex amplitude of the magnetic field, that can be written as, since it's connected with the electric field by the relation E0 over C, I can write B, the complex amplitude of the magnetic field B of Zt as equal to, if I substitute for B0, B0 is E0 by C, so that will be equal to E0 complex amplitude over C exponential I kz minus omega t y. So this is the electric field and this is the magnetic field. Okay, so we are now representing the electromagnetic wave obtained, or electromagnetic wave representing the equations, the two equations that we just saw. We can see here the z direction, the horizontal direction where the electromagnetic wave is progressing, it's advancing, and we can see the electric field pointing in the x direction, varying in x direction sinusoidally, that we can see represented by the arrow marks, the different lobes you can see, and the magnetic field varying in y direction you can see, and the magnitude of the magnetic field or the amplitude is given by E0 by C. So electric field amplitude is E0, the magnetic field amplitude is E0 by C, that is advancing through the advancing in z direction. The velocity is c, that is shown there, the velocity is c, And with regard to electromagnetic wave, we always talk about polarization. Okay, this is a wave that is polarized in x direction, not in z direction. The direction of the electric field, that is the direction of polarization. Here, the electric field is pointing in x direction, so this is polarized in x direction. Okay, so this is how we represent the electromagnetic wave of these two equations. Electric field, magnetic field, electric field pointing in x direction, magnetic field pointing in y direction, electromagnetic wave traveling in z direction. Okay, now this is a particular case. Okay, we are considering the electromagnetic wave traveling in z direction. Actually, we can generalize it to monochromatic plane waves traveling in arbitrary direction, in any direction. Okay, so suppose that the electric field is propagating in the direction of k. Okay, k is a vector which is the propagation vector. We call it propagation vector or wave vector. Its magnitude is the propagation constant k, 2 pi by lambda. So this is the direction in which the electromagnetic wave is advancing, the direction of the propagation vector k. Okay, so we are generalizing. So instead of z direction, here we are taking a wave traveling in the direction of k. Okay, the propagation vector. Okay, and here in the equation we have this kz that we generalize to k dot r instead of kz. So what is r? R is a point, a position vector to a point. Okay, where we want to know the electric field and the magnetic field. Okay, so r is the position vector of a point where the electric field and magnetic field of the electromagnetic wave is to be known. Okay, so I think this is clear. K is the direction in which the wave is advancing, and R is the position vector. In the position of Z, we are not taking R. It's the position vector where we want to know the electric field and magnetic field of the electromagnetic wave. Okay, so see how we are writing the equations. E, vector E, the complex electric field, R comma T. There is a T there, vector R comma T. So the electric field at the position vector R at time T, that is given by E0, the complex amplitude, exponential I. Instead of kz, we have k dot r. Okay, k dot r, the position vector where we want to know the electric field associated with the electromagnetic wave, minus omega t. And instead of x, what we have is n, the unit vector n, the direction of the electric field. So this is the direction of the electric field. Of course, it is perpendicular to k. It's of course it is perpendicular to k. K is the direction in which the wave is advancing. N is a unit vector perpendicular to k, and it is the direction in which the electric field is varying. Then magnetic field will be, E0 by C, magnetic field function of R and T, that is equal to E0 by C exponential I k dot R minus omega t k cross n. K cross n. So that means the magnetic field will be perpendicular to both the electric field and the direction of propagation of the electromagnetic wave. And that is equal to 1 by C k cross E. K cross E. Okay, 1 by C k cross E. Okay, so here the direction of the electric field is in the direction of unit vector n. So we know the direction of the electric field is taken as the direction of polarization. So this is how the electric field is polarized, and n is called the polarization vector. Okay, n is the polarization vector, the direction of the electric field. The electric field is transverse, n dot k is equal to 0, we know. The electric, the unit vector n is normal perpendicular to the direction of propagation of the electromagnetic wave. Okay, so that is shown here. We see a plane here, a plane. We see the k is the direction of propagation of the plane electromagnetic wave. C, the velocity with which that plane is advancing, and we know the r is the position vector corresponding to a point on the plane where we want to know the electric field and magnetic field associated with that particular electromagnetic wave. Then we can see the k dot r. What is k dot r? Unit vector k dot r. Okay, that we know. This is the representation. This is just to obtain an idea about what is k, what is r, and what is the plane, etc. Okay. So now the real electric and magnetic field, the actual electric and magnetic, these are actually the complex forms. Okay, complex forms which have the real part and imaginary part. If you are taking e to the power I theta, we have cos theta plus I sin theta, where cos theta is called the real part and sin theta is called the imaginary part. So for this complex equations, I can take the real part of the electric field and the magnetic field. So I will be getting what? Real electric field and the magnetic field. So if I take the real part of that complex equations, the actual real electric and magnetic field is given by E of RT equal to E0 cos k dot r. Okay, when we take the real part e to the power I theta, the real part is cos theta. So we have this E0 cos k dot r minus omega t plus delta. Delta is an additional phase factor, unit vector in the direction of the electric field. Then B of RT, the real magnetic field, equal to E0 by C cos k dot r minus omega t plus delta, and we know it is k cross n, k cross n. So these are the real electric and magnetic field, and we will be using this real part for the calculations later.